Hi, my name is Sean Skolnick, and I want to tell you a little story about my first experience with the central limit theorem. Basically, I was playing with a calculator when I was a kid, and I came across this dice rolling application. And you actually don't see a dice being rolled on the screen, but what you do see is a resulting histogram being developed. And you, as the user, have the ability of inputting a certain number of times that a dice is going to be simulated being rolled. So for instance, I started off the simulation with 10 rolls, and I in fact did see a histogram that looked like this. Nothing in particularly special. I wanted 4 to win, and I think it did actually win that time, so I was cool. I wanted to see what are the chances that I could duplicate this result, especially if I made n even larger. So then I set n equal to 100, and I wanted to see what the histogram would then look like, and what we got is something that certainly looked like this. It was still nothing particularly special. The bins were all out of sort. I then set n to be some ridiculous number like 10,000, and I just leave it alone because it actually takes a while to simulate 10,000 rolls. And what I then come back to, as it's still going, is a histogram that looks like this. And this was really special because what we have here is that virtually across all the bars are the same, and this really resonated with me as a kid because, of course, no number is more special than the other. It's just a simulation, and those are really something that always really interested me. And probably explained why I went into mathematics. And years later, in my upper division probability class, I come across the central limit theorem, and the central limit theorem says the limit of Sn divided by n as n goes to infinity is equal to mu. So let me explain what all these pieces are. Mu is equal to the expectation of x, which is equal to the summation of xi times the probability density function of x at xi. So let me explain what this x is here. X can represent a particular experiment. In probability, it's called a random variable, but for the purposes of this demonstration, x will be essentially a single dice roll. It will represent just me rolling the dice once. So what the central limit theorem is trying to address is what happens if we have a whole bunch of copies of these same experiments. We have x1, x2, xn, such that they're all they're identically distributed. They have the same distribution. In other words, they have the same probability density function, but they are independent from one another. In other words, the result of the first roll is not going to affect the result of the second roll. So anyways, given that the central limit theorem says this in part, let us find what mu is using this notation right here. So mu is equal to the expectation of x, which is equal to the summation of xi times the probability density function at xi. This turns out to be x1 times the probability density function at x1. We continue this pattern, plus x6 times the probability density function at x6. Substituting in our values right here, we have 1 times 1/6 plus 2 times 1/6, continuing the pattern, we have plus 6 times 1/6. Factoring out a 1/6 from each term, we have 1/6 times 1 plus 2 plus all the way to plus 6. 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. 21 divided by 6 is 3.5. 3.5 is the magic number. 3.5 is our expectation associated to rolling an equal-sided or a fair 6-sided dice. So that's what we need to pay attention to here. Okay? Now Sn is what I'm going to be calling our summation function. It's basically summing up the results of each of these experiments. And then now what I'm going to, Sn divided by n is what I'm going to be calling our averaging function. Okay? So the limit as n goes to infinity of Sn divided by n is equal to mu. Okay? So now that we have these histograms up here, I want to demonstrate how we actually compute Sn. Here we have a 10 roll, in this histogram we have 10 trials, and this is the 1 bin, 2, 3, 4, 5, and I've gone ahead and just roughly calculated how many were recorded in the 1 bin. We have 1 for the 1 bin, 1 for the 2 bin, 2 for the 3 bin, 3 for the 4 bin, and 3 for the 5 bin. And actually we didn't get any results for the 6 bin, that's why we only see 5 bars right here. So that means Sn is equal to 1 times 1, 2 times 1, 3 times 2, 4 times 3, 5 times 3, and if we add up all these numbers, we get 36. So that means our averaging function at the 10th step, S10 divided by 10, is equal to 36 divided by 10, which is equal to 3.6. I continue this procedure for n equals 100 rolls, and I get 3.58. I continue this procedure for n equals 1,000 rolls, and I get 3.579. I then, so what have I done? Now what I can do is I can construct a table of values, and when we're first learning how to do limits in our introductory calculus class, what we do is we first construct a table of values, and what we can see is that for large values of n, we are in fact getting closer to 3.5. So we can go ahead and say that the limit as n goes to infinity of s of n divided by n is in fact 3.5, which is mu, which is the expectation of this experiment, which confirms the central limit theorem. So that is the grand takeaway. Essentially, there are a lot of philosophical takeaways with this theorem. I mean, we've all heard the expression, practice makes perfect. Basically, mathematics justifies this with the central limit theorem. I mean, basically, through the power of repetition, are we able to achieve something idealistic? And that's it. Thank you very much.